The strength of an acid in Arrhenius definition. The Bronsted-Lowry definition refers to its ability or tendency to donate hydrogen cation. A strong acid is one that completely ionizes in a solution. In water, 1 mole of a strong acid HA dissolves, yielding 1 mole of H+ and 1 mole of the conjugate base, A-. Essentially, none of the non-ionized acid HA remains. Examples of strong acids are hydrochloric acid, hydroiodic acid, hydrobromic acid, perchloric acid, nitric acid and sulfuric acid. In aqueous solution, each of these essentially ionizes 100%. In contrast, a weak acid only partially dissociates. Examples in water include carbonic acid and acetic acid. At equilibrium, both the acid and the conjugate base are present in solution. Stronger acids have a larger acid dissociation constant and a smaller logarithmic constant than weaker acids. The stronger an acid is, the more easily it loses a proton, H+. Two key factors that contribute to the ease of deprotonation are the polarity of the HA bond and the size of atom A, which determines the strength of the HA bond. Acid strengths also depend on the stability of the conjugate base. While Ca measures the strength of an acidic molecule, the strength of an aqueous acid solution is measured by pH, which is a function of the concentration of hydronium ions in solution. The pH of a simple solution of an acid in water is determined by both Ca and the acid concentration. For weak acid solutions, it depends on the degree of dissociation, which may be determined by an equilibrium calculation. For concentrated solutions of strong acids with a pH less than about 0, the Hammett acidity function is a better measure of acidity than the pH. Sulphonic acids, which are organic oxyacids, are a class of strong acids. A common example is p-toluene sulphonic acid. Unlike sulfuric acid itself, sulphonic acids can be solids. In fact, polystyrene functionalized into polystyrene sulfonate is a solid strongly acidic plastic that is filterable. Superacids are acid solutions that are more acidic than 100% sulfuric acid. Examples of superacids are fluoroantimonic acid, magic acid and perchloric acid. Superacids can permanently protonate water to give ionic, crystalline hydronium salts. They can also quantitatively stabilize carbocations. Strong acids in water. In aqueous solution, a strong acid is an acid that ionizes completely by losing one proton. According to the equation RH++ A-, the proton lost is captured by a water molecule to form a hydronium ion, so that the equation is more correctly written as Ha plus H2OH3O plus A- for sulfuric acid, which is diprotic. The strong acid designation refers only to dissociation of the first proton H2SO4H++ HSO4-. More precisely, the acid must be stronger in aqueous solution than hydronium ions, so strong acids are acids with a pKa less than -1.74. An example is hydrogen chloride, for which pKa equals -6.3. This generally means that, in aqueous solution at standard temperature and pressure, the concentration of hydronium ions is equal to the concentration of strong acid introduced to the solution. Due to the complete dissociation of strong acids in aqueous solution, the concentration of hydronium ions in the water is equal to the total concentration of the acid introduced to solution. H+ equals A- equals Ha, totaling pH equals -log H+. No acid species stronger than H3O+ can exist in aqueous solution, as any stronger acid is converted to H3O+. The acidity of the stronger acid is said to be level to the acidity of hydronium ion. Strong acids are distinguished from weak acids, in which dissociation is incomplete and is represented as an equilibrium, not a completed reaction. The typical definition of a weak acid is any acid that does not dissociate completely. The difference separating the acid dissociation constants of strong acids from all other acids is so great that this is a reasonable demarcation. Determining acid strength. The strength of an acid, in comparison to other acids, depends on several characteristics. Electronegativity. The higher the electronegativity of a conjugate base in the same period, the more acidic. In other words, the more electronegative A is, more acidic. Atomic radius. With increasing atomic radius, acidity also increases. For example, hydrogen chloride and Hi, both strong acids, ionize 100% in water to become their respective ionic constituents. However, Hi is stronger than hydrogen chloride. This is because the atomic radius of an atom of iodine is much larger than that of a chlorine atom. As a result, the negative charge over the I-anion is dispersed over a larger electron cloud and its attraction for the proton is not as strong as the same attraction in hydrogen chloride. Therefore, Hi is ionized more readily. Charge. The more positively charged a species is, the more acidic. Equilibrium. The strength of an acid can be defined by the equilibrium position of its dissociation reaction. Ha plus H2O H3O plus A-. In a strong acid, equilibrium lies far to the right, meaning that almost all of the original Ha is dissociated at equilibrium. A strong acid yields a weak conjugate base, so a strong acid is also described as an acid whose conjugate base is a much weaker base than water. Common strong acids. This is a list of strong acids with pKa less than -1.74, which is stronger than the hydronium ion, from strongest to weakest. Perchloric acid HClO4, hydroiodic acid Hi, hydrobromic acid HBr, hydrochloric acid hydrogen chloride, sulfuric acid H2SO4, p-toluene sulphonic acid organic soluble strong acid, methanase sulphonic acid liquid organic strong acid. Almost strong acids. These do not meet the strict criterion of being more acidic than H3O+. Although in very dilute solution they dissociate almost completely, so sometimes they are included as strong acids. Hydronium ion H3O+. Hydronium is often used as an approximation of the state of protons in water. Nitric acid HNO3. Chloric acid HClO3. Some chemists include bromic acid, perbromic acid, iodic acid, and periodic acid as strong acids, although these are not universally accepted as such. Extremely strong acids. Fluoroantimonic acid H, SBF6. Magic acid FSO3H, SBF5. Carborane superacid H. Fluorosulfuric acid FSO3H. Trifolic acid CF3SO3H. Weak acids in water. Most acids are weak acids. A weak acid is an acid that dissociates incompletely, releasing only some of its hydrogen atoms into the solution. Thus, it is less capable than a strong acid at donating protons. These acids have higher pKa than strong acids, which release all of their hydrogen atoms when dissolved in water. Examples of weak acids include acetic acid and oxalic acid. Dissociation. Weak acids ionize in water solution to only a moderate extent, that is, if the acid was represented by the general formula Ha. Then in aqueous solution a significant amount of undissociated Ha still remains. Weak acids in water. Dissociators. The strength of a weak acid is represented as either an equilibrium constant or as a percent dissociation. The equilibrium concentrations of reactants and products are related by the acid dissociation constant expression. The greater the value of Ca, the more the formation of H+ is favored, and the lower the pH of the solution. The Ca of weak acids varies between 1.8 times 10⁻16 and 55.5. Acids with a Ca less than 1.8 times 10⁻16 are weaker acids than water. The other way to measure acid strength is to look at its fractional dissociation, which is symbolized as alpha and which can range from 0% less than alpha less than 100%. The dissociation ratio is defined as unlike Ca, alpha is not constant and does depend on the Ha. In general, alpha will increases, Ha decreases. Thus acids become stronger as they are diluted. If acids are polyprotic, then each proton will have a Ca. For example, H2CO3 plus H2OHCO3 minus plus H3O plus has two Ca values because it has two acidic protons. The first Ca value is 4.46 times 10⁻7 and the second is 4.69 times 10⁻11. Calculating the pH of a weak acid solution. The pH of a solution of a weak acid depends on the strength of the acid and the other components in the solution. In the simplest case, the weak acid is the only compound in water. Below is a table that organizes the information. On the first line, the reaction is written. On the second line, the initial conditions are written below each compound. Note that a value of water is not given because its term in the expression is technically equal to 1, but is often omitted. The third line shows how the value changes as the reaction goes to equilibrium. Then the last line gives the equilibrium concentrations and is simply the sum of each column. Applying the equilibrium line to the expression yields rearranging yields, which can be solved for Ex using the quadratic equation. The pH is then calculated as simplification. However, if F is more than 1,000 times Ca, then the acid will not deprotonate much, the value of X will be small, and therefore F(xF). This is also known as the 5% rule. This simplifies the Ca expression too. Solving for X yields then the pH equals log H plus. The following equation then follows, but is only true if F greater than Ca. Comparison of the full and simplified methods. A certain weak acid has a Ca equals 1 times 10⁻5 and the pH of two solutions needs to be found. One solution has a concentration of 0.10 m and another has a concentration of 5 times 10⁻4 m. The pH for both solutions will be calculated using both methods to yield four values, which will be compared. 0.1 m solution. The full method gives the following quadratic, which gives X equals 9.95 times 10⁻4 m and a pH equals 3.00. The simplified method gives, so both methods yield the same result, but again F is more than 1,000 times Ca. The next case does not have this condition and the results will differ. 5 times 10⁻4 m solution. The full method gives the following quadratic, which gives X equals 6.6 times 10⁻5 m and a pH equals 4.18. The simplified method gives here, the results differ by 0.03 picohenries units. As F becomes closer in value to the Ca, then the difference will increase even more. However, in practice, it is rare to work with such dilute acids and the pH is also dependent on ionic strength and temperature. So in reality, the simplified method works well. Conjugate acid-base pair. It is often stated that the conjugate of a weak acid is a strong base. This statement can be misleading. Most weak acids that textbooks discuss have weak conjugate bases. Truly, only the very weakest of acids have strong conjugate bases. For example, if a weak acid has a Ca equals 10⁻5, then its conjugate base would have a Kbe equals 10⁻9, which certainly is not a strong base. A very weak acid with a Ca equals 10⁻20 would indeed have a strong conjugate base. Factors determining acid strength. Polarity and the inductive effect. Polarity refers to the distribution of electrons in a bond, the region of space between two atomic nuclei where a pair of electrons is shared. When two atoms have roughly the same electronegativity, the electrons are shared evenly and spend equal time on either end of the bond. When there is a significant difference in electronegativities of two bonded atoms, the electrons spend more time near the nucleus of the more electronegative element, and an electrical dipole, or separation of charges, occurs, such that there is a partial negative charge localized on the electronegative element, and a partial positive charge on the electropositive element. Hydrogen is an electropositive element, and accumulates a slightly positive charge when it is bonded to an electronegative element such as oxygen or bromine. As the electron density on hydrogen decreases, it is more easily abstracted. In other words, it is more acidic. Moving from left to right across a row on the periodic table, elements become more electronegative, and the strength of the binary acid formed by the element increases accordingly. The electronegative element need not be directly bonded to the acidic hydrogen to increase its acidity. An electronegative atom can pull electron density out of an acidic bond through the inductive effect. The electron withdrawing ability diminishes quickly as the electronegative atom moves away from the acidic bond. The effect is illustrated by the following series of halogenated butanoic acids. Chlorine is more electronegative than bromine and therefore has a stronger effect. The hydrogen atom bonded to the oxygen is the acidic hydrogen. Butanoic acid is a carboxylic acid. As the chlorine atom moves further away from the acidic OH bond, its effect diminishes. When the chlorine atom is just one carbon removed from the carboxylic acid group, the acidity of the compound increases significantly compared to butanoic acid. However, when the chlorine atom is separated by several bonds, the effect is much smaller. Bromine is much more electronegative than either carbon or hydrogen, but not as electronegative as chlorine. So the pKa of 2-bromobutanoic acid is slightly greater than the pKa of 2-chlorobutanoic acid. The number of electronegative atoms adjacent to an acidic bond also affects acid strength. Oxoacids have the general formula OX, where X can be any atom and may or may not share bonds to other atoms. Increasing the number of electronegative atoms or groups on atom X decreases the electron density in the acidic bond, making the loss of the proton easier. Perchloric acid is a very strong acid and completely dissociates in water. The singly bonded oxygen bears an extremely acidic hydrogen atom, which is easily abstracted. In contrast, chloric acid is a weaker acid, though still quite strong, while chlorous acid and hypochlorous acid acids are weak acids. Carboxylic acids are organic acids that contain an acidic hydroxyl group and a carbonyl. Carboxylic acids can be reduced to the corresponding alcohol. The replacement of an electronegative oxygen atom with two electropositive hydrogens yields a product which is essentially non-acidic. The reduction of acetic acid to ethanol using LiAlH4 and ether is an example of such a reaction. The pKa for ethanol is 16, compared to 4.76 for acetic acid. Atomic radius and bond strength. Another factor that contributes to the ability of an acid to lose a proton is the strength of the bond between the acidic hydrogen and the atom that bears it. This, in turn, is dependent on the size of the atoms sharing the bond. For an acid Ha, as the size of atom A increases, the strength of the bond decreases, meaning that it is more easily broken, and the strength of the acid increases. Bond strength is a measure of how much energy it takes to break a bond. In other words, it takes less energy to break the bond as atom A grows larger, and the proton is more easily removed by a base. This partially explains why hydrofluoric acid is considered a weak acid, while the other hydroallic acids are strong acids. Although fluorine is more electronegative than the other halogens, its atomic radius is also much smaller, so it shares a stronger bond with hydrogen. Moving down a column on the periodic table, atoms become less electronegative but also significantly larger. and the size of the atom tends to dominate its acidity when sharing a bond to hydrogen. Hydrogen sulfide, H2S, is a stronger acid than water, even though oxygen is more electronegative than sulfur. Just as with the halogens, this is because sulfur is larger than oxygen and the H-S bond is more easily broken than the H-O bond. Acids in non-aqueous solvents. The strength of an acid also depends on the solvent basicity, so that acids which are strong in water may be weak in less basic solvents, and acids which are weak in water may be strong in more basic solvents. According to Bronsted-Lowry acid-base theory, the acidity of an acid H in a solvent S is due to the acid-base reaction H plus Sa- plus Hs plus. For example, the solvent glacial acetic acid is less basic than water, and the extent of ionization of the hydroallyl acids varies in the order H greater than HBr greater than hydrogen chloride. These acids lose a proton to a CH3COOH molecule, which forms its conjugate acid, CH3COOH2+, but the reaction is only partial. In contrast, these three acids are all strong in water. Acetic acid is said to be a differentiating solvent for the three solute acids, while water is not. An example of a solvent more basic than water is liquid ammonia, NH3, in which acids react to form the ammonium ion. H plus NH3 to A minus plus NH4 plus. In this solvent, acetic acid is solute as a strong acid and ionizes completely, and has the same strength as hydrogen chloride, which is 1,000 times stronger than the strength of sulfuric acid, is entirely non-corrosive, whereas the weak acid hydrofluoric acid is corrosive and can dissolve, among other things, glass and most metals.